Here we talked about vectors in the plane and the cable tension force. And so recorded from trigonometry, if we have a unit circle, this is a circle with radius 1. And so this segment right here will have a length of 1. And in the unit circle, and if we form the right triangle right here, then the length of this side will be cosine of theta, where theta is the angle from the positive x-axis to the hypotenuse. So it's this angle right here. And so this side will be cosine of theta, this side will be sine of theta. And therefore this point right here will have the x-coordinate of cosine of theta, and the y-coordinate will be sine of theta. And now let's talk about the vector unit vector. And so here I have a unit vector, we have a unit vector u. And again, the angle theta is formed by the positive x-axis and the vector. And so this is the angle theta right here. And once again, the length from here to here is cosine of theta, and the length from here to here is sine of theta. And therefore this point right here, which is the terminal point of the vector u, the coordinates will be cosine of theta, sine of theta. And therefore we can write that the vector u, which is a unit vector since its length is 1, will have components of cosine of theta and sine of theta. And so this is what the unit vector in terms of theta is. And now what we want to show that for any non-zero vector, then the vector v divided by the magnitude of v is also a unit vector. And so here I have we have the vector v. And so if we do vector v dividing by the magnitude of v, and we want to show that that is a unit vector. And so let's call this vector right here, the vector v divided by the magnitude of v, we'll call it u. And we want to show that u here is a unit vector. And so the magnitude of u, which is the magnitude of v divided by the magnitude of v. Record that the magnitude of a constant times a vector is the absolute value of the constant times the magnitude of the vector. And so here we have this vector v dividing by the magnitude of v, which is the same as 1 over the magnitude of v times v. And therefore 1 over the magnitude of v is a positive constant. And so it's just a constant. And so we can write this as the absolute value of 1 over magnitude of v times the magnitude of v. And 1 over the magnitude of v times the magnitude of v is just 1. And also notice that 1 over the magnitude of v is positive. And so here we have u is equal to a positive quantity times the magnitude of v. And therefore u and v will have the same direction. And graphically, this is what it looks like. And so this is the vector v. Then the vector v divided, this vector right here, v divided by the magnitude of v will be this unit vector right here. But the unit vector can be written in terms of theta as the vector with components cosine of theta times sine of theta. And from here we multiply both sides by the magnitude of V. Then we get V is equal to the magnitude of V times this vector right here, which is the, and then we could also rewrite it as magnitude of V times cosine of theta, and then comma magnitude of V times sine of theta. And then we could also write this vector V right here as linear combinations of standard unit vectors. And so this can also be written as magnitude of V times cosine of theta times I, where I is the standard unit vector 1, 0, and then plus the magnitude of V times sine of theta times J, the vector J, where J is the standard unit vector 0, 1. And so graphically, this is what they look like. So this is the vector V right here, and then this is the unit vector U, which is V dividing by the magnitude of V. And this is the standard unit vector I. This is the standard unit vector J. And so we can write V, this vector V right here. V is the linear combination of magnitude of V times cosine of theta times I, plus magnitude of V times sine of theta times J. And so this is this vector right here, the vector magnitude of V times cosine of theta times I. This is the horizontal component of vector V, and it's this vector right here. This is the vector magnitude of V times cosine of theta times I. And then the vector magnitude of V times sine of theta times J is this vector right here. And this is the vertical component of vector V. So vector V can be written as the linear combination of the horizontal component plus the vertical component. So for any non-zero vector, we can express it as a linear combination of the horizontal component and the vertical component. And once again, the angle theta is the angle between the positive x-axis and the vector. And so it's this angle right here. And if we have a vector in that ends up in the second quadrant like this, then the angle theta will be from the positive x-axis to the vector. And so the angle theta would be from here to here. And here we have an object that has a mass of 50 kilograms, and that is hung from two cables. And so it would be this cable and this cable. And we want to find the tension force in each cable. So we have cable number 1, cable number 2, and cable number 3. And we want to find the tension force in each one. And so notice that this cable right here, the tension force is acting downward. And for this cable, call it cable 1, the tension force is acting in this direction, upward like this. And so the tension force in this cable, some of it will be upward and some of it will be to the right. And then for this cable, the tension force will be is acting in this direction. And so some of the force will be to the left and some of it will be up. And so once again, we want to find the tension force in each cable. And so let's look at cable number 1. And so think of this as a vector. And this angle right here is 60 degrees. And so let's go ahead and draw the x-axis right here. And then the y-axis will be from here to here. And so here we have the x-axis, and here we have the y-axis. And so this angle right here is 60 degrees. And therefore this angle right here will also be 60 degrees. And so for cable number 1, or for vector number 1, vector t1, t sub 1 here, we can write this as the t sub 1 can be rewritten, written as a linear combination of the standard unit vectors I and j. And so the vector t sub 1 is equal to the magnitude of t sub 1, which is what we're looking for, since we want to find the tension force in each cable. So it'll be the magnitude of t sub 1 times cosine of theta, which is the 60 degree angle right here, 60 degree, and then plus the magnitude of t sub 1 times sine of theta, or sine of 60 degrees. And so this is the vector t sub 1, which is this vector right here. And once again, the tension force is acting in this direction. And for t sub 2, or for this vector right here, this angle is 45 degrees, and therefore this angle right here is also 45 degrees. And therefore for this vector, the theta will be from here to here, which is 135 degrees, because this angle right here is 45, and so from here to here would be 135. And so we can write vector t2, t2 as the magnitude of t sub 2 times the cosine of 135 degrees plus magnitude of t sub 2 times the sine of 135 degrees, and then times the standard vector unit I and the standard unit vector j. And then for this vector right here, the vector t sub 3, the tension force is acting downward, and therefore the weight of this object will be the mass times the gravity. And since it's acting downward, we have the negative right here. So it'd be negative 50 kilograms times the 9.8 meter per second squared. And since it's downward, the direction will be the times j, which is the standard unit vector, 0, 1. And therefore we get negative 490 newtons. And to write this vector right here in terms of I and j, and then we can write this as 0I minus 490 j. And since we have a system here that's in equilibrium, then we know that the forces, the sum of the forces must be equal to 0. And so t sub 1, t sub 2, t sub 3, the sum of the forces must be equal to 0. And so this is the t sub 1, this is t sub 2, and this is t sub 3. It must be equal to the 0 vector. And then combining all the, and then we can write this as magnitude of t sub 1 times cosine of theta plus magnitude of t sub 2 times cosine of 135 degrees, and then times I. And then for the terms with the vector j, we can write it as magnitude of t sub 1 times sine of 60, magnitude of t sub 2 times sine of 135 minus 490. And then the zero vector, we can write it as 0, the scalar 0 times I plus the scalar 0 times j. And therefore we have to have this part right here is equal to the scalar 0, and then this expression right here is equal to the scalar 0. So let's call this equation 1 and call this equation 2. And then from the equation 1, we solve for magnitude of t sub 2. And so we get negative magnitude of t sub 1 times cosine of 60 degrees dividing by cosine of 135 degrees. And then on the calculator, we do cosine of 60 degrees dividing by cosine of 135 degrees. This is what we get negative. We get a negative number. And then since we have a negative right here, negative makes it positive. And so this is what we end up with. And then now for equation 2, if we solve for the magnitude of t sub 1, then we get negative magnitude of t sub 2 times sine of 135 degrees plus 490 dividing by sine of 60 degrees. And then in the place of magnitude of t sub 2, we replace it with this. And then now on the calculator, if we do negative 0.7071, all of this right here, times sine of 135 degrees, dividing by sine of 60 degrees, then we'll end up with this number right here. 490 dividing by 60 degrees, then we'll get this. Move this term right here, move it to the right. And so this term here, move it to the right, and this is what we get. Magnitude of t sub 1 is the same as 1 times the magnitude of t sub 1. And then these are like terms, and so 1 plus 0.5735 is what we get here. And then dividing both sides by 1.5735, then we'll end up with 358.70. And so the tension force in the magnitude of the tension force in the first cable will be 358.7 newtons. And then the tension force in the second cable will be 0.701 times this number right here, and we'll end up with 253.64 newtons. And so once again, the tension force in here, in this cable, is 560, it'd be 358.7, and then the tension force in this cable will be 253.64. And of course, for this cable right here, the tension force will be the 490 newtons that we got earlier.